team at Astra. Our team name Ad Astra, in all honesty, is the name of a sci-fi movie starring Brad Pitt. But upon further research, we found out it translates to "thus one goes to the stars" or immortality, which to us signifies the hopeful immortality of space exploration. After 4 weeks of vigorous and extensive hard work, we are finally ready to present our project for the third cohort of Junior Space Scientist Program, calculating and refining the Hubble constant. So, to introduce the team behind this project, we have firstly our team leader, Pratyu, who is in grade 11 and lives in Chennai, our co-leader, Avni, who's in grade 8 and lives in Bangalore, Vaivahi, who's in grade 12 and lives in Assam, Drone, who's in grade 12 and lives in Delhi, Tia, who's in grade 10 and lives in Hyderabad, Lakshana, who's in grade 10 and lives in Chennai, and myself, Sarisha, who's in grade 11 and lives in Mumbai. So to give a brief about what we will be going through in this presentation, first we have why the Hubble constant, where we will be explaining why we chose our topic for this project and what we hope to contribute to it. The procedure, where we will be explaining the methods we use throughout this research. The learnings, where we will be reflecting upon all the knowledge we've gained throughout the course of these 4 weeks thanks to this program. And finally, the end of credits to express our utmost gratitude to everyone involved in this project.
The universe is everything, from the grains of sand to the elements that make up all living beings. It's all we've ever known, and what lies within its endless boundaries has always fascinated the best of us. Some of our earliest conceptions of the universe were sketched onto the caves of our ancestors. Here we see that this is a dough of raisin bread with 3 raisins spread apart by 5 and 10 centimeters. After it's baked, we see that it increases in size from 20 to 40 centimeters, but now it's spread apart by 10 and 20 centimeters. We can say this is the case because the speed at which these raisins move away from one another is constant, and therefore their distances are proportional to one another. This logic can be applied to the expansion of our universe. With the launch of the Hubble telescope, scientists have calculated the approximate rate at which the universe expands, and this term is called the Hubble constant.
Thank you, dear. To understand redshift, we first need to investigate the phenomena of the Doppler effect. In a sense, the Doppler's effect is the apparent difference between the frequency at which sound or light waves leave a source and that at which they reach an observer, caused by the relative motion of the observer and the wave source. It is the reason why the frequency of sound emitted by an ambulance seems to increase as it approaches us, and the frequency of a train horn seems to decrease when it moves away from us. Now, of course, the above examples were for cases involving sound waves. The same principles also work for light waves, and this can be denoted by 2 standard phenomena, namely redshift and blueshift. Light behaves like a wave, and so light, or more precisely electromagnetic waves from a luminous object undergoes a Doppler-like shift if the source is moving relative to us. A redshift is an increase in the wavelength and a corresponding decrease in the frequency for electromagnetic waves. This occurs when the source or the observed phenomena, whether that be a galaxy or an exoplanet, moves away from us. Conversely, an opposite movement, that is the source or the observed object, is moving towards us, is known as blueshift. Now over to Lakshana.
Hi everyone, this is Lakshana. I'm currently studying in 10th grade and I'm from Chennai, Tamil Nadu. So my part of this presentation is the cosmological distance ladder. So first of all, what is the cosmic distance ladder? The cosmic distance ladder, also known as the extragalactic distance scale, is the series of methods by which astronomers determine the distances of celestial objects. Distances with the solar system are known to extreme accuracy till date by a variety of methods, including the motions of planets in the star, radar, and the timing of signals from interplanetary probes, which are nothing but satellites. The techniques for determining distances to more distant objects are all based on various measured correlation between the methods at close and large distances. This ladder has rungs of objects with certain properties that let astronomers confidently measure their distance. This allows them to move outward and measure even greater distance rung by rung. So, the cosmic distance ladder and the methods for measuring the distance. The two major methods for measuring the distance are geometric methods and standard candle methods. The geometric method, as it says, is how we measure the distance using geometry. It contains radar distances and parallax. And the standard candles. Standard candles are astronomical objects that has known brightness. So by comparing this luminosity to an object's brightness, the distance can be easily computed. Standard candles contain spectroscopic parallax, also known as the main sequence fitting, Cepheid variable stars, and type 1a supernovae. Spectroscopic parallax, also known as main sequence fitting, despite its name, it doesn't really rely on geometric parallax effect. The method of measuring the colors and brightness of many stars and comparing them to the colors and luminosities of a known set of stars is referred to as the spectroscopic parallax. This technique of spectroscopic parallax will give the distance to any star for which a spectrum can be obtained. This is the most important one and permits distance determination even into nearby galaxies several million parsecs away. Cepheid variable stars. In 1912, Henrietta Swan Leavitt, an astronomer, noted that 25 stars called Cepheid stars that would brighten and dim periodically like an inflating and a deflating balloon. By observing the apparent luminosity dimmed by the inverse square law of light, comparing this with the predicted luminosity, astronomers can calculate the distance to the star. Type 1a supernovae is a special type of supernovae as their light curve exhibit the sharp maximum. Type 1a supernovae are some of the best ways to determine extragalactic distances. It is a type of supernovae that occurs in a binary system, which is two stars orbiting one another, in which one of the stars is a white dwarf. Their consistent peak luminosity allows these explosions to be used as a standard candle to measure the distance to their host galaxies. Thank you. Now handing it over to Avni.
Thank you, Lakshana. Now, I would like to give you a glimpse of our thought process or the thinking behind the research. So first, in order to determine the Hubble constant, we mainly needed two things: the distance to various celestial objects and their recessional velocities, or redshift. Hence, we started our search to find suitable standard candles and explored several candidates, including quasars, galaxies, and supernovae, due to their high luminosity and relatively common occurrence in the cosmos. In the end, however, we used a combination of numerous supernovae, quasars, and a few galaxies to find our value. After completing this, we began searching for specific celestial objects, all within a distance range of 1,000 million light years, or 1 billion light years. We chose this specific distance range and realized that we couldn't use the redshift method of calculating distances beyond that extent effectively. It is a capital mistake to theorize before one has data. This is a quote by Arthur Conan Doyle that could give us an insight into the next slide. After figuring out our standard candles, we started researching to find out their distances in order to compare them with the results we calculate and to make sure that they fall in their range, their redshifts, an essential part of the equation, and their absolute and apparent magnitudes in order to calculate their distances. We use sites such as the NASA ADS website and the NASA IPAC Extragalactic Database in order to find reliable and credible information. We also adopted a method of cross-checking the information we find in order to minimize and prevent errors. A few examples of how we documented our findings: the first column being the names of the standard candles, the second one being the distances that we calculated, the third one being the distances that we found, and the fourth one being the redshifts. I would now like to hand it over to Baibabi to give us an insight into the distance modulus equation. Thank you.
Thank you, Avni. So to calculate the distances to the objects that we selected, we could not go ahead with the methods described in the cosmological distance ladder because we discovered that the distances to our objects were incredibly large. So after a lot of research and discussions with the team, we finally decided to go ahead with the distance modulus equation as the most ideal method to calculate the distances to our objects. So the distance modulus basically measures distances on a logarithmic scale based on an astronomical magnitude system. So in astronomy, magnitude is nothing but the brightness of something. And distance modulus is basically the difference between the apparent magnitude, which is denoted by small m, and absolute magnitude, which is denoted by capital M of an object. Now, you might be wondering what are these apparent and absolute magnitudes, right? So apparent magnitude is of an object is basically the brightness of an object observed from Earth. And similarly, absolute magnitude is the brightness of the object observed from a certain standard position. Now, if the distance modulus, which is small m minus capital M, is equal to 0, it basically means that the object is exactly 10 parsecs away from us. And if the distance modulus is negative, it basically means that the object is closer than 10 parsecs away. And similarly, if it is positive, it means that the object is 10 parsecs further away from us. Now, for our project, we basically found out the values of the apparent magnitudes and absolute magnitudes of our objects from various sources. We also calculated the absolute magnitudes for certain objects that we could not find data for online. And finally, we substituted those values into our distance modulus equation you could already see it in the screen, which is apparent magnitude minus absolute magnitude is equal to 5 log function of r by 10 to base 10, where r gives the distance to our object. So we calculated our distance through this equation and finally found out the distances of all our objects. Now, I would like to turn the mic over to Pradyum so that he could put some light on how we use this distance values as well as redshift values to calculate our Hubble constant. Over to you, Pradyum.
Thank you, Baibabi. Good evening, all. I'm Pradyum Bharat Kumar, and I'm going to be presenting about how we plotted the graph using Python. So first, let us take a look at the code first. We as a team shortlisted 3 types of standard candles, namely supernovas, quasars, and galaxies. We calculated the distance by using the distance modulus formula, and we got values which were really close enough to the actual ones. So the x-axis consists of the distances and y-axis consists of the radial velocities. We store these values in a variable, and then we converted the distance into parsecs by multiplying by 0.306601. We converted the redshift into radial velocities. So then we printed the Hubble's value and got a final value about 84.25. We use matplotlib, which is a comprehensive library for creating static, animated, and interactive visualization in Python. Now let us take a look at a graph. So here, the x-axis represents the distance, the y-axis represents the radial velocity, the straight blue line represents the Hubble's constant, the red dot represents the supernova, the triangle represents the quasars, and the star represents the galaxies. Over to you, Tia.
Thank you, Pradyum. So over the course of this project, our main motive was to determine the Hubble constant. Alongside that, we had also gathered enough data to determine when the expansion of the universe began, which gives us the age of the universe. Before I explain how we calculated it, I'd like to establish a couple key equations that we used that helped us calculate the age. So the key assumption made was that the universe is expanding with a constant velocity. On the screen here, we see 2 diagrams. Let's assume that the left circle is our universe about 10 billion years ago, and the right diagram is our universe right now. Like said, the universe is expanding with a constant velocity, so the edge of the circle can be considered as the time or the age of the universe. The magnitude between the central point of the circle and the edge of the circle can be considered as the distance. As we can see, the distance would be equal to the velocity into the time. Because time is the key factor that we're trying to determine, we would rearrange the equation such that t is the subject. So our new equation would be t is equal to d by v. The second equation, which is the Hubble's law, states that velocity is equal to the Hubble constant into the distance. So we'd substitute this value of the velocity into our time formula, which would give us t is equal to d by h naught into d. Because d is effectively the same value, they cancel each other out to give rise to 1. And our final equation is t is equal to 1 by h naught, which is the reciprocal of the Hubble constant. Now, the second step is to convert all our values to a standard unit and then apply this to our key equation as discussed previously. As Pradyum mentioned, the value that we calculated for the Hubble constant was 84.26 km per second per megaparsec. In this, we will convert the kilometers and megaparsecs into meters. To convert the kilometers into meters, we will multiply 84.26 into 10 to the power 3 because 1 kilometer is equal to 10 to the power 3 meters. To convert the megaparsecs into meters, we will first have to convert the megaparsecs into parsecs and the parsecs into meters. We use the value 10 to the power 6 to convert the megaparsecs to parsecs, and we will multiply that by 3.1 into 10 to the power 16 to convert it to meters. The value that we get finally is 2.72 into 10 to the power minus 18 second inverse. Now, a common question that would be asked is, if the Hubble constant is a unit of velocity, how did we end up with a unit of time? The Hubble constant is a unit of velocity, but it can also be represented as 1 by t, which is nothing but 1 by s, or second inverse. Applying this to our key equation that we mentioned in the previous slide, t is equal to 1 by h naught. As we saw, h naught is about 2.72 into 10 to the power minus 18. So once the substitution is done, we get our answer as 1 by 2.72 into 10 to the power minus 18 second inverse. So our answer would be 3.68 into 10 to the power 17 second inverse. We'd have to divide this value by 365 into 24 into 60 into 16, because this part of the equation helps us convert the seconds into years, which is a more understandable unit of time. The value we get after carrying out this operation is 1.167 into 10 to the power 10 years, which finally gives us the value of 11.66 billion years as the age of the universe. I'd now like Agni to deliver the vote of thanks.
Thank you, Tia. We are a team of 7 students bound by an unyielding fascination for cosmic exploration and are yet separated by vast distances. However, through diligent collaboration over a multitude of Google Meets, we have ventured to address one of astronomy's most significant and contentious insights, the Hubble constant. Over a rigorous period of 4 weeks, we dedicated ourselves to this task and ultimately arrived at a value of 84.26. We hope that this contribution might aid in shedding light upon the myriad of mysteries that the universe continues to withhold. Thank you, and I would like to hand the mic over to Sarisha. So that was it for our presentation. And finally, we would like to give our vote of thanks, starting off with SSRD, who are the ones who organized the entire JSS program and gave multiple young space enthusiasts like us an opportunity of a life. Special thanks to the SSRD organization team and Nishita ma'am, who put in so much effort for us and made sure the program carried on without any hazels. Next, I would like to thank our respected mentors, beginning with Nikita ma'am and Tejas sir, who conducted multiple insightful training sessions which are bound to help us for our life and our careers. Next, I would like to thank our mentor Siddharth sir, who was a guiding light to us during the entire project and helped us anytime we stumbled. Thank you. Without any of you, this would not have been possible.
Thank you, Team Ad Astra. That was wonderful work that you've done, and the way you presented as well is amazing. I would like to, congratulate Siddharth on this for the amazing work that the students have done. And I can see the kind of effort that's been put by the mentor in this team. Thank you so much. I would now leave the stage open for questions. In case if you have a question, you can unmute yourself or you can raise your hand and then I would give in a chance for everyone. I have a question to your team. So the constant that we found here in this project, now, would it be different after a certain amount of time if you calculate, or has this been, as the name suggests, being constant throughout? It might be a very dumb question too, but I'm just curious to know.
It will be a constant value because it's the rate at which the universe is expanding. So the distance between two objects will increase over time, but the rate at which it is expanding, which is basically the Hubble constant, will not change.
Okay. Probably a follow-up question. So we found this Hubble constant now. Did you all explore where we could use this Hubble constant, or which are the different domains of research where we could use this Hubble constant, or astronomers or astrophysicists can use this Hubble constant?
As such, ma'am, I don't think we specifically focused on this, but of course we can use this as a future project that we all can take up.
And also, as we used it in the presentation, we can use it to calculate the age of the universe, which is something a lot of us are granted in.
Right? Can we use this constant to extrapolate and find the how big the universe could be, let's say after 1 million years of time?
Yeah, we could.
Yes.
Okay, now that's a lot of questions from my end. Even the other teams can come in and like post your questions or just unmute yourself and ask if you have any questions.
Yeah, I had a question. You people said that you will be able to calculate the age of the universe, and which you did, which was something around 11 billion years, right? But the one that we actually know states that 13.8 billion years. So why is there such a difference in the two values?
So the value that we got was like our research had certain limitations as well, and we are not saying that, but this is something that we got within the frame of time and the work that we did. So our research definitely has certain limitations. So yeah, I think that answers.
I think normally, what's normally accepted as the Hubble's constant is between 69 to 75 kilometer per second per megaparsecs. But then, due to the scope of the limitation that we had over the course of our research, we arrived at a slightly larger value, which is the lower end of 80s, and therefore that contributed towards the difference between the two values.
I'd also like to add to that point. We used the redshift method, which allowed us to stretch only to about 1 billion light years when the universe is about, like, we wanted to stretch it out to about 14 billion. So I think that span of distance might really made it. That was again a limitation, like Baibubi and Dhruv pointed out.
Thank you.